So now we've talked about how to prepare aldehydes and ketones by either oxidation of alcohols with carbon-6 reagents or milder manganese-4 reagents if they're oleic or benzoic or propargylic. We've talked about oxidative cleavage of alkenes. We've talked about hydration of alkynes using either anti-Markovnikov or Markovnikov conditions. And we've talked about Friedel-Crafts acylation and the related Catherine-Koch reaction. How do they react? So the rest of chapter 17, we talked about reactions of the carbonyl group of aldehydes and ketones. And these reactions will all be nucleophilic acyl addition reactions. So if you have a general nucleophilic acyl addition mechanism in mind from the first semester, we're going to be talking about a lot of nucleophilic acyl addition reactions. In the first semester course, the only type of nucleophilic acyl addition reaction we talked about were reactions with strongly basic reagents. All right, so let's start there with review. Strongly basic reagents. And in particular, sources of negatively charged hydrogen or negatively charged carbon. Hydride or a carbon anion. Now, obviously, we don't just use hydride or CH3 minus, because if we did use those species, they're strong enough basic, so all they would do is deprotonate at the alpha position. So we have to attenuate their basicity a little bit to get them to be a softer base that's more able to attack the carbonyl-carbon. But fundamentally, we're talking about hydrogen and carbon anions. And we're talking about hydride reducing agents. And we're talking about organometallic reagents. Within hydride reducing agents, we have two different sets of conditions. We have lithium aluminum hydride, which is reactive enough that it can only be used in an inert solvent such as ether, and then requires a second aqueous acid hookup step. And we're talking about sodium borohydride, NaBH4, which is enough less reactive that you can actually put the proton source in the same mixture by running it in alcohol salt. So we have our source of H minus, and then we have our alcohol as our source of H plus. And effectively what we're doing is adding H minus to the carbon of the carbonyl group and H plus to the oxygen carbonyl. And then within the organometallic reagents, we're talking about alkyl lithiums, like CH3Li, or we're talking about Grignard reagents. Like, say, phenylmagnesium bromide, which is actually the Grignard reagent that we're going to be making and using in the first lab of this semester, where we do a Grignard addition to 2-methylcyclohexanol. So, alkyl magnesium bromides are alkyl lithiums, and you may remember that alkyl lithiums are made directly from alkyl halides by adding 2 equivalents of lithium solid. The other product then being lithium bromide, and alkyl magnesium bromides are made from the corresponding alkyl or aryl bromides, in this case benzene, by simply adding magnesium solid, and forms a 2+ ion and inserts itself into that carbon-bromine bond. Both of these reactions need to be done in an inner solvent. And this reaction is the one that we're going to be doing in the first week of the lab, where we'll take bromobenzene and add magnesium solid, magnesium turnings, and make phenyl Grignard for subsequent reaction to the carbonyl group. So, depending on the identity of the carbonyl group, you can make a variety of alcohols. So, with the hydride reducing agents, for example, we can convert aldehydes into primary alcohols. Or we can convert ketones into secondary alcohols. And these reagents are interchangeable for now. Sodium borohydride does in fact have different reactivity than lithium aluminum hydride. So there are some reactions that lithium aluminum hydride will do that sodium borohydride will not. For instance, reducing esters. Lithium aluminum hydride will reduce esters to primary alcohols as well, where sodium borohydride will not. But for now, for the purposes of aldehydes or ketones, you can use either of these sets of reaction conditions interchangeably. And generate primary alcohols from aldehydes or secondary alcohols from ketones. The mechanism of that reaction is quite straightforward. The aluminohydride, which is technically has a negative formal charge on aluminum, will donate one of its hydrogen atoms to the positively polarized carbon. These reactions are not reversible. To generate salt, and then in the second step, the aqueous acid will protonate that alkoxide ion to generate the alcohol. So it's a nucleophilic attack at the positively polarized carbon, followed by an acid-base reaction to protonate the negatively charged oxygen. A strongly basic reagent will react readily with the positively polarized carbon, and remember that if you're in doubt, you can always write the minor resonance structure, which has a formal positive charge on carbon and negative formal charge on oxygen, and then should make it obvious to you this carbon is subject to attack by the hydride ion. If we were to use just plain old lithium hydride, because hydride ion associated with lithium is much more ionic, there's a bigger electronegativity difference, it would simply deprotonate here in the alpha position to generate the helium. So we have to make it a little bit less basic by attaching it to a metal with a higher electronegativity value than the alpha metals. The mechanism for sodium borohydride is similar, except that it's just a single step, where the proton is coming off the ethanol at the same time as the hydride is donating. chloride is donating, pi bond is breaking and picking up hydrogen or ethanol to generate BH3. In this case, propanol. And the corresponding ethoxide ion of free radical ethanol is the solvent. And we have the sodium counter ion floating around. There'll be an acid workup step for sodium borohydride reductions, but it won't be required to generate the alcohol. It will be required to neutralize the alkoxide ion that's generated from the solvent. So we can make either primary or secondary alcohols. We can make tertiary alcohols by hydride reduction because a tertiary alcohol has no hydrogen attached to the carbon bearing the alcohol, and the hydride reagent donates a hydrogen to that carbon. But we can make primary, secondary, or tertiary alcohols from organometallic reagents, depending on what we start with. Again, for our purposes at the moment, the alkyl lithiums and the alkyl magnesium bromides are interchangeable, and you can use them equivalently. There are some cases, and we'll see one later in the semester, where alkyl lithium and alkyl magnesium bromide reagents will actually have different reactivity. But for now, you can use whichever one you want. So, for example, we can take methyl lithium, and that bond is about 40% ionic. So there's approximately a positive 0.4 charge on lithium and approximately a negative 0.4 charge on the carbon, right? It's not a full negative charge like it would be if it were attached to sodium or potassium. If it were a full negative charge, it would do an acid-base reaction to generate phenolate, but it's enough covalent, more covalent than ionic, that it softens that up. If we react it with formaldehyde, the product will be a primary alcohol. First step is simply to treat it with the alkyl lithium, ether, or THF. THF this time, since we use ether exclusively. And then an aqueous acid workup. And once again, the intermediate is an alkoxide ion. This is a powerful reaction because it's a carbon-carbon bond forming reaction. And apart from the palladium catalyzed coupling reactions that we covered right at the end of the first semester course, you don't know a lot of carbon-carbon bond forming reactions. And then in the second step, we do proton transfer from the aqueous acid to generate our primary alcohol. So formaldehyde as the reagent, with an organometallic, primary alcohol as the product. If we use an aldehyde and an organometallic, the product will be a secondary alcohol. UCC bond. In this case, acetaldehyde. Right, so just a plain old aldehyde, secondary alcohol. Mechanism is the same. Nucleophilic attack at the carbon-carbon. We do step 1. Generate the alkoxide ion, and then the alkoxide ion gets propagated to generate the alcohol. Formaldehyde, primary alcohols, ordinary aldehydes, secondary alcohol, and ketones will generate tertiary alcohols with organometallic reagents. And the reaction you're going to actually be doing in the lab will take 2-methylcyclohexanone and treat that with phenylmagnesium bromide and ether solvent, followed by workup with this acid. Your source of the acid will actually be ammonium chloride, aqueous solution of ammonium chloride. Mechanism will be the same. Phenylmagnesium bromide attacking the carbonyl oxygen. You'll notice these reactions are not reversible. So you form that carbon-carbon bond, it's not coming back off. And then the alkoxide ion in our case, instead of reacting with aqueous acid, it's actually going to react with the ammonium ion, so the milder acid. Generate two-methyl 1-phenyl cyclohexanone. So all of these reactions are fairly straightforward. They're just two steps. A nucleophilic source of either H- or carbon minus is going to attack the carbonyl carbon, generating an alkoxide ion as an intermediate, and then that will be protonated in the second step with an acid workup, either plain old aqueous acid, like 1 molar or 2 molar HCl, or in this case, ammonium chloride. Because we don't want to dehydrate that alcohol, and because it's a tertiary allylic alcohol, it dehydrates quite readily. So if we use a stronger acid, we risk forming alkyl products, which is what we want to do in the second week of the laboratory, well, actually the third week, the second week we're going to purify that alcohol. But we don't want to do it prematurely. With sodium borohydride, that's the one exception here. We don't have an acid workup step as our proton source. We actually use a protic solvent, usually an alcohol, ethanol or methanol, as our proton source. So the nucleophilic attack on the carbonyl carbon and the protonation of the oxygen in that case happen simultaneously in a single step. So these are the reactions you already know. Strongly basic reagents, irreversible, kinetically controlled, forming a new carbon-carbon bond or a new carbon-hydrogen bond. The remainder of the reactions that we're going to talk about in this chapter are under acid catalysis and mostly reversible.